Something extraordinary is unfolding in our solar system, and it has captured the attention of nearly every major space agency on Earth. The interstellar visitor known as **3I, Atlas**, only the third confirmed object ever discovered entering our solar system from interstellar space, has begun behaving in a way that has left astronomers searching for answers. Instead of following the predictable path expected of a natural object, recent observations suggest that its trajectory may have changed in a way that challenges everything we understand about orbital mechanics. For the first time ever, the International Asteroid Warning Network, a global collaboration created to identify and monitor potential threats to Earth, has devoted significant attention to an object that originated beyond our solar system. That decision alone has raised an important question. Why would an organization focused on planetary defense suddenly prioritize an interstellar traveler? The reason appears to lie in a growing collection of unusual observations. According to tracking data examined by astronomers, 3I, ATLAS no longer seems to match the orbital path predicted when it first entered the solar system. Researchers comparing new measurements with earlier calculations noticed discrepancies that could not be easily explained using conventional models. If these measurements are confirmed, the implications are remarkable. A significant change in trajectory during the object's close approach to the Sun would require forces far beyond what scientists normally expect from a comet or asteroid. Such behavior would represent one of the most unusual events ever recorded in modern astronomy. The International Asteroid Warning Network, often called IAWN, exists for one primary purpose: coordinating observations of objects that could pose a risk to Earth. Its members include many of the world's leading observatories and space agencies, working together to share data and improve our ability to detect potentially hazardous objects long before they become a danger. Historically, the network has focused almost entirely on asteroids and comets that formed within our own solar system. Interstellar visitors have been considered scientific curiosities rather than planetary defense concerns. That is why the decision to monitor 3I, ATLAS so closely immediately attracted attention throughout the astronomy community. Officially, the explanation was straightforward. Scientists wanted to improve the precision of measurements collected from a rare interstellar object. Better observations would help refine orbital calculations and expand our understanding of these mysterious visitors from other star systems. However, the timing sparked speculation. Shortly before the announcement, 3I, ATLAS disappeared behind the glare of the Sun during its closest approach. When astronomers prepared for its expected reappearance, several independent observers reported that its position did not perfectly match the forecasts generated before the solar encounter. Even small differences in an object's location can become important when dealing with interstellar trajectories. As additional observations accumulated, some researchers suggested that the deviations deserved closer examination. Others argued they could simply reflect uncertainties in early measurements. The debate quickly intensified. Among those discussing the object was Harvard astrophysicist Avi Loeb, who has long encouraged scientists to remain open to investigating unusual interstellar objects without immediately dismissing unexpected possibilities. His comments reignited public interest and encouraged astronomers around the world to continue gathering more data. Soon afterward, observatories across multiple countries devoted additional telescope time to tracking 3I, Atlas. What had begun as a routine scientific campaign gradually evolved into one of the most closely watched observations of an interstellar object in history. Then another claim began circulating among independent researchers. After comparing fresh telescope measurements with publicly available orbital predictions, they reported that the object's observed position appeared to differ from where existing models suggested it should be. The reported discrepancy was substantial enough to trigger widespread discussion online. Some interpreted it as evidence that something extraordinary had occurred during the solar flyby. Others urged caution, pointing out that interstellar objects often require continuous updates to their orbital solutions as more precise observations become available. Regardless of which explanation proves correct, one fact is undeniable. 3I ATLAS has become one of the most intensely studied objects ever to enter our solar system, and every new observation seems to generate even more questions than answers. As astronomers continued collecting data, attention shifted from simple orbital calculations to the physics that could explain the reported deviations. If the object had truly moved away from its expected path, what mechanism could have produced such a change? Natural comets are not perfectly predictable. As sunlight heats their icy surfaces, jets of gas and dust erupt into space. These outgassing events act like tiny thrusters, producing small changes in speed and direction. Scientists have observed this behavior many times, and it is well understood. However, these forces are generally limited and follow patterns that can be incorporated into orbital models. What made 3I ATLAS so intriguing was the suggestion that its motion might not fit those familiar patterns. Several analysts argued that the reported displacement appeared unusually large compared with what ordinary cometary activity would produce. If true, it would represent an exceptionally rare case requiring much closer investigation. One group of independent observers compared newly released positional measurements with predictions generated before the object's close pass around the Sun. Their calculations suggested that the observed location differed by an enormous distance on an astronomical scale. Although many professional astronomers cautioned that orbital solutions are routinely refined as additional observations become available, the unusual claim spread rapidly through the scientific community and across social media. The discussion soon centered on a critical question. Was the discrepancy simply the result of incomplete data collected during the solar flyby, or had something physically altered the object's motion? If conventional outgassing were responsible, astronomers would expect to detect evidence of asymmetric jets releasing material into space. Those jets could gradually modify the object's orbit over time. But some researchers argued that the reported shift appeared difficult to reconcile with the level of activity observed from the object. That uncertainty fueled a wave of speculation. Some proposed that interactions with the solar environment had temporarily influenced the object's motion. Others suggested that observational errors during the period when the object was hidden behind the Sun might explain the mismatch. More imaginative theories quickly followed, ranging from unknown physical processes to the possibility that the object possessed characteristics unlike any interstellar visitor previously observed. As interest intensified, attention turned toward NASA's Jet Propulsion Laboratory, whose orbital calculations are widely regarded as one of the most reliable references for tracking objects throughout the solar system. Researchers carefully compared updated predictions with fresh observations, searching for any indication that the object's trajectory was evolving in unexpected ways. Meanwhile, astronomers pointed out another curious feature that had attracted scientific interest. Observations suggested that 3I ATLAS displayed an unusual dust structure during part of its journey, including what appeared to be an anti-tail. Despite its name, an anti-tail does not actually point material toward the Sun. Instead, it is an optical illusion created by viewing geometry and the distribution of dust particles along the comet's orbit. Although rare, the phenomenon has been documented in several comets over the years. Even so, every unusual characteristic added to the mystery surrounding the visitor. As more telescopes joined the observing campaign, researchers collected increasingly detailed measurements of its brightness, rotation, composition, and motion. Each new dataset helped improve scientific understanding while also generating fresh debates over what the object might reveal about the environments beyond our solar system. Whether the reported anomalies ultimately proved to be the result of natural physics or simply improved observations, one thing has become clear. 3I Atlas is providing scientists with a rare opportunity to study material that formed around another star billions of years ago. Every image and every measurement could reveal clues about distant planetary systems that humanity has never explored. And as the object continues its journey through our cosmic neighborhood, astronomers remain focused on one goal above all else: separating extraordinary claims from extraordinary evidence. The next observations may determine whether 3I Atlas becomes remembered as an unusual comet, or as one of the most significant astronomical mysteries of our time.